All right, so welcome everyone. We're diving headfirst into the seriously weird, seriously cool world of quantum physics today.
I love it when you say it like that.
Well, get ready because we're talking about a recent discovery that has scientists, well, pretty excited. It's about how those tiny particles in the quantum world, flip between different states.
You mean quantum phase transitions?
Yeah, exactly. And it's kind of like water freezing into ice,
Ah, I see where you're going with this.
But way weirder.
Way weirder, yeah.
But before we get too deep into the mind-bending stuff, we're going to be looking at this article called Physicists Just Witnessed a Quantum Phase Flip, and it's more mind-bending than expected.
Great article. I think everyone should check it out.
Totally agree. So to kick things off, can you give us a quick, refresher on what quantum phase transitions actually are? For those of us who haven't been hanging out in a physics lab lately.
Of course, of course. Well, you're already familiar with phase transitions in your everyday life. It's like, think about water. Water turning into ice, right? Or metal becoming magnetized.
Yeah, totally. Those make sense.
So those are all examples of a system, any system, completely changing its properties as conditions shift, like temperature or pressure. Classic stuff.
Right. Those classic examples make sense. But I'm guessing things work a bit differently in the quantum world, don't they?
Exactly. In the quantum realm, these transitions are governed by, well, the laws of quantum mechanics, obviously. So instead of things like temperature and pressure, we're dealing with some pretty mind-boggling concepts like quantum fluctuations, for example, or entanglement. And get this, the particles themselves, they aren't just bouncing around like billiard balls.
Oh, no.
Nope, they're behaving like waves.
Waves, whoa.
Yeah, existing in multiple states at the same time.
Whoa, okay, so you're telling me these quantum particles are basically playing by a completely different set of rules. That's wild.
It is pretty wild.
The article also mentioned something called dissipative phase transitions.
DPTs.
DPTs, right? What makes those so special?
Okay, so it all comes down to energy loss. Imagine a closed system where energy is perfectly conserved. Okay, got it. Now, in the real world, systems constantly interact with their environment, which means they lose energy through a process we call dissipation.
So kind of like a spinning top, right? Slowly losing energy and kind of wobbling before it finally comes to a stop.
That's a great analogy, yeah. That's a really good one. Now, imagine that happening on a quantum scale, right? That energy dissipation can actually force the system to transition into a totally new phase. And that's what we call a dissipative phase transition, or DPT for short.
Okay, so DPTs are basically quantum systems losing energy and kind of flipping into a new state. But the article mentioned there are different types of these DPTs, right?
You're right. We categorize them based on how they happen. First-order DPTs are like flipping a light switch, abrupt and dramatic. The system jumps from one state to another in an instant.
Dramatic, I like it. And what about the other kind?
Second-order DPTs, well, they're more like slowly turning a dial. They involve a gradual shift in the system's fundamental properties, like its symmetry, for example. It's a subtle change that ultimately leads to a fundamental shift in how the system behaves.
Okay, I think I'm starting to get it. But why are scientists so fascinated by these DPTs? Why should we care about them?
Well, think about it this way. Most of our current technology relies on equilibrium physics, things in a stable state. But imagine the possibilities if we could harness the power of systems operating far from equilibrium, in a constant state of change. That's where quantum technologies come in, things like quantum computers or ultrasensitive sensors.
So DPTs are kind of like the instruction manual for this new quantum era. And you're saying understanding them is key to building these, mind-blowing technologies.
Exactly. Second-order DPTs, for example, could revolutionize how we store quantum information, making it much more stable. And first-order DPTs, they're crucial for figuring out how to control those delicate quantum systems, especially for something as complex as a quantum computer.
Yeah, that makes sense. So let's talk about this recent breakthrough. What did these scientists actually do?
This is where it gets really exciting. Researchers at EPFL, one of the world's leading science universities, have actually managed to directly observe these DPTs in action for the very first time.
Wow, that's incredible.
That's a huge step forward, especially for those elusive second-order transitions.
So how did they manage to pull that off?
They used a highly sensitive device called a superconducting Kerr resonator. Think of it like a superpowered antenna that can pick up the faintest whispers of the quantum world.
I'm picturing it like a super-powered magnifying glass, for the quantum world.
Exactly. They also use a special technique called a two-photon drive to carefully manipulate the quantum state of their system and nudge it towards those phase transitions.
So, but why did they have to go to such extreme lengths? Couldn't they have just observed these transitions under, normal conditions?
Well, to clearly observe these transitions, they needed to minimize any possible interference or noise. Imagine trying to hear a whisper in a crowded room. It's almost impossible.
Yeah, no, that makes sense.
Right. So to isolate the quantum effects they were studying, they had to conduct their experiments at incredibly low temperatures, close to absolute zero.
So ultra low temperatures and this super sensitive Kerr resonator were the keys to unlocking these quantum secrets.
Absolutely. And what they found, it's truly mind-blowing.
You've got me on the edge of my seat here. Don't worry, listeners. We'll be right back to uncover those incredible findings after we'll be right back.
Right back. Okay, so let's dive into these mind-blowing findings.
All right, hit me with it.
In the second-order DPT, they observed something called squeezing.
Squeezing. Okay, I'm intrigued. How does squeezing even work in the quantum world?
So imagine you have a balloon, right, filled with air.
Okay, yeah.
All those air molecules inside are constantly jiggling around randomly.
Okay, makes sense?
Those are like your quantum fluctuations.
I see, okay.
Always buzzing with uncertainty.
So squeezing is like taking that balloon and kind of squeezing it in one direction.
You got it.
Okay, so you're saying the fluctuations get smaller in that direction. But wouldn't that just make them bigger somewhere else?
You're exactly right. You reduce the uncertainty in one variable, but increase it in another.
Okay.
What's remarkable here is that they managed to squeeze those quantum fluctuations to a level even below the natural background noise of empty space.
Hold on, quieter than empty space. How is that even possible? I thought empty space was, well, empty.
It's one of those, one of those mind-bending things about quantum mechanics, right?
Mm.
Empty space isn't truly empty. It's actually teeming with virtual particles that pop in and out of existence, creating a constant hum of quantum noise. But in this experiment, they managed to create a state that's even quieter than that.
Wow.
It's like finding a level of silence deeper than the vacuum of space itself.
That's pretty incredible.
Yeah.
This sounds like it could be a game changer.
Yeah.
But how does it actually help us, build better quantum technologies? How do we actually use this?
So this is a huge deal because it means we can potentially isolate quantum information from all that noisy environment.
Oh.
Making quantum computers much more stable and reliable.
That's huge.
Imagine trying to solve a complex equation on a calculator that's constantly being shaken. Right?
Yeah, you'd never get the right answer.
You'd never get an accurate answer, right? So squeezing could be the key to protecting those delicate quantum states from interference, allowing us to build quantum computers that can actually tackle those mind-boggling problems we've been dreaming of.
That makes perfect sense.
Yeah.
So we've got squeezing in the second order DPT. What about the first order? What did they find there?
Okay, so with the first order DPT, they observed something called metastability.
Metastability.
Think of it like a coin perfectly balanced on its edge, right?
Oh, okay.
It could fall heads or tails.
Right.
But for a brief moment, it's in both states at once.
So the system is basically like stuck in a quantum limbo,
Yeah.
unsure which way to jump.
Precisely. It's a fascinating tug of war between two competing phases, and eventually the system will tip over into one state or the other.
Mm.
And they also observe something called hysteresis in this first order transition.
Hysteresis. All right, now you've got me stumped again.
Okay, think of it like this. Imagine you're stretching a rubber band.
Right.
You pull it and it stretches.
Mm.
But when you let go, it doesn't immediately snap back to its original shape, right?
Right.
There's a bit of a lag.
Yeah.
This hysteresis, the system's current state, depends on its past.
Ah, so it's like the quantum system has a memory of where it's been?
Exactly. It's
Right.
like, the system remembers its history.
That's pretty wild.
Yeah. Now, here's another fascinating thing they observed in both types of transitions. Critical slowing down.
Critical slowing down.
Okay.
Hit me with it. What's that all about?
Imagine a ball rolling down a hill.
Okay.
As it gets closer to the bottom, it slows down dramatically.
Right, yeah.
That's kind of what happens in critical slowing down.
Mm-hmm.
As the system approaches that point of transition, its response to any changes slows down dramatically.
So it's like the quantum system is taking its sweet time to make up its mind.
You got it. And this phenomenon has been, predicted theoretically,
Yeah.
but actually seeing it confirmed experimentally, that's a big deal.
Right.
It helps validate our understanding of these transitions.
Okay, I see why that's important. But is there more to it than just confirming what we already thought?
You're right. There's more to it.
Okay.
Think about it. This slowing down could be incredibly useful for making ultra-precise measurements.
Oh, okay.
Imagine being able to slow down a process to study it in exquisite detail.
Yeah.
It's like taking a slow-motion video of a hummingbird's wings.
I see what you mean, that slowing down could allow us to study these transitions with much more precision.
Yeah.
Potentially leading to, even more sensitive quantum sensors.
Exactly.
Okay, cool.
Now let's step back for a moment.
Okay.
We've talked about squeezing, metastability, critical slowing down.
Right.
All these, amazing phenomena observed in these DPTs.
Right.
What's the big takeaway here? What does it all mean?
Okay, that's a lot to take in.
Sure.
I'm trying to wrap my head around it all.
Yeah.
I guess for me, the biggest question is how do we go from observing these, mind-bending transitions in a lab
Right.
to actually building those incredible quantum technologies we've been talking about?
That's the million-dollar question, isn't it?
It really is.
These findings are like a roadmap, giving us a deeper understanding of how to, manipulate and control these delicate quantum systems.
So it's like we've been handed the blueprint, and now it's time to start building.
Precisely. The next step is to take this newfound knowledge and apply it.
Right.
We need to explore new materials, refine our control techniques, and really push the boundaries of what's possible in engineering.
Yeah.
This is where the real adventure begins.
Okay, so we've journeyed deep into the quantum realm
Yeah.
and explored some truly mind-boggling phenomena.
Mind-boggling, yeah.
Squeezing, metastability,
Critical slowing down.
critical slowing down. It's amazing to see how scientists are, pushing the boundaries of what we thought was possible.
It is pretty amazing.
Really is.
And let's not forget the incredible implications of all this, right?
Yeah. What are those again?
I mean, we're talking about quantum computers that
Yeah.
that could crack problems that are currently way beyond our reach.
Right.
Sensors that could detect the faintest signals imaginable.
Yeah.
The possibilities are truly vast.
It's moments like this that I'm reminded of how much we still don't know about the universe.
It's true.
It's both humbling and incredibly exciting.
Yeah, I agree.
So where do we go from here? What are the next steps in this quantum adventure?
Well, even with these breakthroughs, there's still so much we don't know about DPTs.
Really?
Oh yeah. We need to explore how all sorts of different quantum systems behave under these conditions. Are there universal principles governing these transitions, or are there even more surprises waiting to be uncovered?
Oh, that's so cool.
So it's a wide open frontier.
I love a good quantum mystery.
Me too.
So what else is on the horizon for this?
Another exciting avenue is figuring out how to, harness these transitions for practical applications.
Yeah.
Can we use squeezing to create ultra-sensitive quantum sensors that can detect things like gravitational waves or tiny changes in magnetic fields? Can we exploit metastability to build more robust quantum memories that can store information for much, much longer periods? These are just a few of the challenges that researchers are tackling right now.
It sounds like we're just scratching the surface of what's possible.
I think so.
Who knows what other quantum wonders are out there just waiting to be discovered.
Exactly. And that's what I find so inspiring about this field.
Yeah.
Every new discovery opens up a whole new set of questions and possibilities, pushing us to think differently and challenge our assumptions about how the universe works.
It's enough to make your head spin, but in the best possible way.
The best way.
So to our listeners out there, what are your takeaways from our deep dive into the quantum world? What's stuck with you?
Yeah, what excites you about the potential of these new technologies? What questions are swirling in your mind right now?
Yeah, we encourage you to dive deeper into this fascinating field, explore the research, and let your curiosity be your guide.
The quantum world is full of wonders waiting to be uncovered, and who knows, maybe you'll be the one to make the next groundbreaking discovery.
Until next time, keep exploring the quantum frontier.